Hey there, team. Ready for video number 10. Technically, really number 6 because we did 4 review ones. So, video number 10. All right. We're going to be looking at work per se, right? So, does it make sense that if electrons are moving from the anode to the cathode, right, they're moving around, that's going to generate energy, okay? So when those electrons are moving in a spontaneous voltaic cell, that movement of electrons generates energy. Let's call that work per se. So we're going to end up deriving an equation here. So if you look back in thermodynamics, they looked at the Gibbs free energy change. They used to call it free energy change. It's the amount of free work produced. I think it was negative, like the work was the negative of the delta G or something like that. So we're going to end up relating thermodynamics to electrochemistry through this concept of the work done from movement of electrons. That amount of work from the movement of electrons is really determined by 3 factors, if you think about it. And, I'm the master of horrific analogies. So let's think about that waterfall, a dam, analogy again. The potential difference, the driving force for those electrons to go from the anode to the cathode, that's akin to the height of the dam or the height of the waterfall, right? The higher up, the more driving force there is, the more potential there is. So hopefully that makes sense, right? The more positive the E cell, the more work we can get out of it because the more driving force we have for electrons to go from anode to cathode. Well, the number of electrons being transferred, right? That's akin to the amount of water flowing over the dam or over the waterfall, right? The more water you got, the more energy you can get from it. We call that the electron number. It's a unitless value. We call it Z. They used to call it N, but people get confused with moles of electrons. So we're just calling it Z, the electron number. And I just mentioned in the last video, you have to really look at the anode and cathode half reactions, the oxidation reduction half reactions, combine them and see what's the total number of electrons transferred in that process. Is it 6? Is it 4? Is it 2? Is it 1? That's the electron number. Right? Number of electrons transferred from cathode to anode. And then lastly, the amount of electric charge per mole of electrons. So if we have a mole of electrons being transferred, what's the electric charge on it? And the unit of that's the coulomb. I introduced the coulomb earlier, and I think I gave you the charge of a single electron with some 1 to 2 times, like negative 1 to 2 times 10 to the minus 19th coulombs for a single electron. Well, if we do it for a mole of electrons, just take that 10 to the minus 19th times Avogadro's number, right? 6.022 times 10 to the 23rd, and you get Faraday's constant. So I wonder who did this one. Oh, Michael Faraday. Hey, one of the more important scientists ever. So we get this value. It's a constant. I'll provide you that all the time. And I don't actually, it's not going to matter if it's exact or not. With 5 significant figures, that's more than we're ever going to need. So that'll never limit your calculations. So Faraday's constant, or capital F, is 96,485 coulombs per mole. Right? Coulombs per mole. And you can think of that as akin to the gravitational constant in my horrible analogy of the energy we can get from a dam. How high is the dam? How much water is going over? And what's the gravitational accelerational constant? Boom. Let's put those 3 things together. Let's put E cell. We could do it for, that'd be non-standard. We could also do it for standard conditions. Let's put the electron number in there, and let's put the Faraday's constant, the amount of electric charge we can get out of a mole of electrons there. And let's do some equations. Yay, we like equations. Ready to do some algebraic manipulation, my friends? So let's put those things together. So the work, or amount of energy we can get from these flowing electrons, is the electron number, Faraday's constant, and the cell potential. Boom! And again, we could have that as standard condition. But from thermodynamics, like I said, work was the negative of the Gibbs free energy, or the Gibbs free energy was the negative of the work. It comes from that. So that has work in it. Oh, that has work in it. Oh, so mustn't that equal to that? Would you do that for me? Equate those together and solve for an equation for delta G. All right. Therefore, they must equal each other. So if work equals negative delta G equals ZFE cell, oh, I dropped my cap. Delta G, move the negative sign over, is negative the electron number times Faraday's constant times the cell potential. And that would be for non-standard conditions. So anything other than 1 molar, right? And we could have done exactly the same thing for standard conditions, so let's do that as well. So delta G naught at standard conditions will be negative the electron number times Faraday's constant times the cell potential at standard conditions, everything with an activity of 1 or molarity of 1. And that is standard conditions. Now, since we have not looked at non-standard conditions yet, we're obviously going to be using this equation. And this is a fantastic equation because this allows us to connect thermodynamics to electrochemistry. Oh, we're getting somewhere now. Just wait till we get equilibrium in the mix. It's like Three's Company. All right, so we just got 2 to tango here. We'll get to Three's Company later. We could use the values from our electrochemical table, right? So if I could give you any reaction, you could use values from this electrochemical table, right, to calculate E cell. That's a constant, Faraday's constant, 96,485 coulombs per mole. Z is the electron number you get from the half reactions and combining them. Couldn't we determine delta G values at standard condition just by using electrochemical tables? And vice versa, couldn't we use thermodynamic tables, right? Especially if we're at 25 degrees Celsius. Nice, we could go straight to thermodynamic tables, calculate delta G at standard conditions. If it's not at 25 degrees Celsius, it's doable, but pain in the butt. You'd have to calculate delta H naught, delta S naught, plug it in to our, what is it, delta G is delta H minus T delta S naught. Oh, it seems like forever ago we were doing thermo. So we could calculate that. And then given from that and this, we could determine E naught cell without actually measuring it, right? So we can use tables to find E naught cell to get delta G, right? Or vice versa. We could use thermodynamic tables to find delta G, and then we could calculate E naught cell. And of course, you can see the spontaneity of this process. We know E cell or E naught cell has to be positive to be spontaneous, right? And if that's positive, that's positive, that's positive, that's negative, delta G or delta G naught is negative when E cell is positive. Makes sense. That's why spontaneous reactions have negative G. Got that from the second law of thermodynamics. And E cells are positive. Yay! Let's do an example, my friends. All right. This is a type of question you would expect to see on a quiz or an exam. Of course, I would give you the electrochemical tables. Here we go. Use electrochemical tables to determine the change in Gibbs free energy at standard conditions for the following reaction. Of course, I was being a poopy head, and I gave it to you as a cell line notation. So we're going to have to extract the oxidation half reaction and the reduction half reaction from this. Look up those values on the table, right? Of course, we got to reverse the anode and change the sign on it. Well, let's see if we can extract it from here. Well, you know, you pause it and see if you can do it. Of course, remember, the anode's always on the left. Cathode's always on the right. So this is your anode half reaction, the oxidation half reaction. This is your cathode half reaction, the reduction half reaction. Of course, these are both ions, so we need the iron solid. Oh, no, we can't have iron solid there. Ha, 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 because that might react. That would have been confusing because that could have actually reacted. We don't want that electrode to react, so we're going to have to get platinum there as a non-reacting electrode because we want the iron 3 to be reduced to iron 2, not to iron solid. Ho, 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 ho. Have at it. I'm going to pause this, give you a few minutes to see if you can do the reduction and oxidation half reactions, add them together, right? You make sure the electrons match out, give me the overall equation there, and figure out what Z is. And then find the individual electrode values, add them together, and get E naught cell overall. And if you're feeling up to it, use that equation. If you know E naught cell and you know the electron number Z, multiply that by Faraday's constant, you got delta G, my friend. Give it a shot. Let's see how you did on the first part. Nothing new with the first part. You just go through what we've said. What's the oxidation, what's the reduction half reaction? What are the E cells? reverse the anode, change the sign, add them together, right? Make sure the electrons are equal, and then add the two. So it's the same thing over and over and over, all right? So go through and do that first part, end up getting the E naught cell, and then now we're just adding that equation where we take that times the electron number times the Faraday's constant. That's it, no big deal. Give it a shot. Let's walk through this. Hopefully you did the second part. All right. Gave you the line equation. We know this is our anode. So our oxidation will be the copper solid to the copper plus 2 at standard conditions. And if you don't see the concentration written there, we kind of assume it's 1 molar, because if it wasn't, we'd write it and we know we're not at standard conditions. So not required to always put the 1 molar there. Sometimes I can't fit it on my board. So, and then of course that'll be giving off 2 electrons. So I looked for that on here. I was looking for the copper right there. So there's the copper plus 2 electrons going to copper solid, which is the opposite of that. Remember, these are reduction potentials, so we have to reverse that copper equation, so we have to put a negative sign in front of the 0.340 there. That's why I've got the negative sign. Oh, you like my new Father's Day shirt? Oh, hold the door, hold the door, hold the door, hold the door, hold the door. You're a Game of Thrones fan. All right, anyway. Now, this is our cathode, our half reaction there. So we're reducing the iron 3 to the iron 2. That's why I had to get rid of the iron solid for the electrode. We can't use iron solid. We have to use platinum. So the iron 3 is picking up 1 electron to form iron 2. So we have to find that. And that's the reduction. So that's directly off of here. So if we look on here, you can see right there, there's iron 3 plus an electron going to iron 2, 0.771 volts. Straight up reduction, boom. Now when we add these together, remember we have to make sure the electrons cancel. 2 electrons there, 1 electron there, they don't equal each other, so the common multiple is 2. So I have to multiply my reduction half reaction by 2. That's why you have the times 2 there. And again, this is these electropotentials are intensive properties. Doesn't matter if you multiply it by 2. That still stays as 0.771 volts. The height of the waterfall doesn't change if you double the amount of water going over it. All right. So we're going to get 1 mole of copper solid, 2 moles of iron 3 ions, 2 moles of electrons, giving us 1 copper 2 ion, 2 iron 2 ions, and then 2 electrons, which then cancel out. So Z, the electron number, will be 2 in this particular problem. We're going to need that to calculate the Gibbs energy change. So Z is 2. That's a unitless number. It's the electron number. So now we've got our overall equation. Let's add the cathode to the anode to get overall cell. So the cathode is 0.771 volts, good to 3 decimal places. The anode is the reverse of what was on the reduction table. So the negative of 0.340 is negative 0.340 volts, also good to 3 decimal places. So I get 0.431 volts. That is the overall cell potential at standard conditions for this, which would be spontaneous. So I would expect my delta G to be negative. Plug it into that equation. Let's have at it. So this is kind of a 2-part problem. You'll get, the more you do this, the faster you'll get at it. Here's the equation. Now, I would give you this equation on a quiz or exam. You just have to know when to use it. And again, we could go both ways. In this case, we're using electrochemical tables to calculate this to get the thermodynamic delta G. I could flip this around, right? Maybe I always write 2 exams, A and B. So maybe A, I have you do it this way, but B, I have you use the thermodynamic tables to calculate delta G and then solve for E naught cell. Ha, tricky. Here we go. Let's plug in our values. Now, one thing you'll have to worry about is delta G values, if you remember, are usually kilojoules per mole. So let's see how these units, there's going to be a little hitch in here. I'll show you how to get around. All right, we've got the negative. What was our electron number? It was 2, right? There was 2 electrons transferred through. That's an ugly looking 2. Faraday's constant I'd give you, 96,485. Coulombs per mole. So how are we going to extract stuff out of here? Times E naught cell, what was that, 0.431 volts? Is that right? Now I'm looking at that going, yeah, well, I'm going to get coulombs times volts per mole. What? So, but we have to understand what is a volt. If you remember when we introduced that early on, it was the energy per unit charge, right? So a volt is a joule per coulomb, correct? So we're going to have to rewrite volts. Now you can either just erase volts and put joules per coulomb, or you could just do a quick little thing like this and go a volt is a joule per coulomb, if you want to do that. Or if you just want to erase V, put joules over coulombs, coulombs cancels that, put you directly in joules. I don't care which way you do that, but can you see the volts cancels? This will be inverse coulombs, leaving you with joules per mole. And of course, Gibbs energy is typically kilojoules per mole. So let's convert joules to kilojoules. So 1,000 joules per kilojoule. Whoop. And that allows us to cancel out joules. So that'll leave us kilojoules per mole. Yay! And since E naught cell was positive, I would expect this to be negative, right? So positive, 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 positive. See the negative sign there? We shouldn't be surprised we get a negative delta G, which makes it spontaneous. Let's see, we've got, that's an exact number. The electron number is an exact number. Faraday's constant, we don't have to worry about. That's got like 5 minimum. It's the voltage that's always going to limit you here. So we got 3 significant digits in our voltage, so we're going to get 3 significant digits in our answer. So delta G naught to 3 sig figs, I get negative 83.170 kilojoules per mole. So we got the right units. Now, if I just asked for delta G like in this one, you could have left it as joules per mole, which would be a weird number, right? Like 83,000 something, you'd be like, wow, that's awfully big. But if I don't specify the units, you could leave it as joules per mole. But I would like to have you understand it's typically as kilojoules per mole. So it's like delta H, delta G, kilojoules per mole. But delta S is usually joules per mole Kelvin, right? That's going to round up. So that'll be negative 83.2 kilojoules per mole. And because that is greater, that is negative, so delta G naught is less than 0, we know this baby is spontaneous, right? And we could say E naught cell is greater than 0. Yay! It all falls together quite nicely. Welcome to the negative sign. So that's work. So what's nice about this is everything was the same we'd done before. We just added one new equation using this work to connect thermodynamics and electrochemistry. So it's a beautiful equation we have here. Provided for you on exams. Yay! Let's move on to the next video. Yeah!